value store. And the rather crude examples we've looked at so far with our customer and our order scenario have really been of this type. So as you can see in the first sub-bullet there, rather than having a column called name, you would instead, within a particular row, you might have a key of name with a value of Andrew. And just because you have that in one row doesn't necessarily mean it's going to appear in the next one, which kind of underlies the point that key value stores are schema-free. You can have different keys in each row. Typically, all the rows in a table will have at least a similar structure, but they actually don't really have to. They can be completely different. Key value stores are the most common type of NoSQL database, and as it turns out, the other three types are often implemented using key value stores as the underlying infrastructure. It's just that they create a certain level of abstraction on top of what a key value store does. Here are some examples of key value store products: Riak, Redis, Windows Azure Table Storage, Amazon Web Services, SimpleDB and DynamoDB, Dynamite, and Voldemort. Next, we've got document stores, and these are really interesting because instead of having rows, basically, you have documents. And the documents really turn out to be JavaScript objects. They're encoded using something called JavaScript Object Notation, or JSON, and the JavaScript language ends up being used as the internal language for these databases as well. All of these technologies are extremely familiar, almost second nature to any kind of a serious web developer. And as such, document stores tend to be very applicable to web applications, because suddenly the static content in a website and the actual data driven content ends up having an awful lot in common, and the distinction between the two kind of, I wouldn't say it goes away, but it definitely gets blurred. Document stores are schema-free as well. CouchDB and MongoDB are probably the two absolutely most prominent examples of a document store. Wide column stores are a different kind of a NoSQL database in that they are not schema-free. They are semi-structured. You need to specify groups of columns known as column families, but not the actual columns within those families. So the actual columns can differ from row to row, but the column families, which clearly kind of imply a certain category or domain of data, do need to be declared when the table is designed. Apache HBase, which is part of virtually every single Hadoop distribution out there, is the most prominent. Cassandra, I won't say it's a close second, but it's a significant second. All of these are open source products, except of course the cloud platforms, Windows, Azure, and Amazon Web Services. Otherwise, all of these are open source products. Graph databases are the last type and probably the most specialized. They really focus on the relationships between entities rather than especially being focused on the representation of the entities themselves. There's a product called Neo4j that is the one that comes up again and again when you're discussing this category. Graph databases tend to be extremely useful for social media applications because of the necessity to track relationships between people. In fact, the reason that your network of friends is called a social graph ought to tell you a little something about why graph databases are so applicable in those cases. So that's our summary. Next, we're going to take a look at more concrete examples of each of these four. So let's start by looking at key value stores. Again, this is the most prevalent kind of NoSQL database that's out there. And let's just state explicitly from here on that it is possible with all of these types of NoSQL databases to vary the schema from row to row. In these examples, we're actually not going to illustrate that because we just really want to focus on the way that the data is managed the hierarchy and the structural containers, if you will, that have the data and the vocabulary used to refer to it. And vocabulary, speaking of vocabulary, key value stores have pretty friendly vocabulary because it actually mimics exactly what we have on the relational side of things. So we have a database, and the database has tables. And here we have a customer table and an order table, just kind of like we did before. We're going to kind of have data that's a bit different than the early examples in this course, though. So we've got one row here. It has an ID of 101, and it's got a few keys in it: first name, last name, address, and last order. Here's another row, and again, we're keeping the structure constant, but you don't actually have to do that. Now, we do see that the last order for customer 101 is 1501, and the last order for customer 202 is 1502. And, handily, we have those two orders shown here in the example as well. But there's no explicit relationship between the two. Just as we said earlier on, these things exist rather independently, and the way you need to connect them is by, in effect, creating your own foreign keys and through your own programmatic conventions, recognizing that a foreign key links to a primary key in another table. Let's take a look at wide column stores and see how they differ. Now, wide column stores have tables. Notice the tables don't belong to a database. There is no such thing as a database. There are just tables. And the tables have rows. The rows have super columns and then columns within them. So the super columns are defined when the table is defined. You have to declare your super columns, in this case, name, address, and orders. But then on a row-by-row basis, you can declare the columns or keys within those super columns. So we've got first name and last name within name. We've got number and street within address, and we have last order within orders. Likewise here, notice it's the same data as the previous example. And on the order side, it's the same data as well. Here we can imagine having a pricing super column, which happens only to have one regular column in it, and we have an items super column that has two item IDs in it as well. And we can imagine those relating out to, let's say, a products table. All right, let's continue on by looking at the document store category of NoSQL databases. And in this case, we're not going to build out the slide. Most of these relationships are fairly familiar from what we've seen before, but there are some nuances here that we do want to point out, and we'll highlight those as we go through the slide. Now, just as with our wide column store, you'll notice customers and orders are standalone containers that have no overall parent. In this case, though, they're not called tables, they're actually called databases, but conceptually they function just like the tables inside of key value stores and inside of wide column stores. Instead of containing rows, they contain documents, but again, conceptually the documents are similar to rows. They have key and value pairs just like they would inside a key value store. What's a little different here, though, is that the value of a key can actually itself be a document. So if you take a look on the upper right-hand corner, that customer document 101 has an address key, and the value of that key is itself a document with keys and values for number and street. You'll also see that the orders key has a document as its value, and that document in turn has a key called most recent, and the value of that key actually points to another document in another database, in this case, the order document 1501. So we can actually have hierarchical relationships, and we can have relationships between documents, even if they're in different databases. And so we have kind of more creature comforts with the document store in terms of application development than we might with some of the other NoSQL database types. The last of the four subcategories we need to look at are graph databases. Now, get ready for some different vocabulary here. We start with something familiar. We start with a database, but from there on, it gets rather different. We have what we call a node, and in this case, that node is Andrew Brust, We have another node which has 4 different properties in it: street, city, state, and zip. And between those 2 nodes, we have an edge. And the edge is given a relationship name of address. In effect, this is really kind of an edge that represents a property. So Andrew Brust has an address, and that address in turn has 4 properties and values of its own. But Andrew can also have a simple relationship to another node in the database that represents a person. In this case, I'm a friend of George Washington. I've sent an invitation to Jane Doe, and I've commented on a photo by Joe Smith. So you'll see that what we're doing here is not just sort of putting people inside of a table of people, but rather we can have heterogeneous types of data, and we can relate them through the edges. And we can also have more of a hierarchical relationship here. In this case, Andrew Brust placed in order, and that order has its own properties and values as well. So we can absolutely represent the same customers and orders that we've had in the other scenarios, but we also have the ability to have multiple people here, in effect customers, I suppose, and we can relate them very easily. So you can absolutely see why this type of database is so applicable to social media applications.